So here we have an equation, the second derivative of the vector valued function r with respect to t, and that's equals to negative n squared times vector r. We have to integrate this given equation. So let's begin. We'll come back to the integration in a moment. First, we'll have to talk about few definition. So let's say we have a vector r dotted with itself. Now we want to take its derivative with respect to t. What will be its value? So this will be equals to, so we'll have to use the product rule here. So we'll take, let's call it the first function, and this is the second function. So we have derivative of the first function, the first vector valued function, and this will be dotted to the second function, plus we'll take the first function and dot it with the derivative of the second function with respect to t. Now we know that the scalar dot product is commutative in nature, so that means these two are exactly the same term. So that can be also written as 2 times vector r dotted with dr vector over dt. So this is the derivative with respect to t of vector r dotted to itself. So let's call it equation number 1. Next, what we'll do, we'll use the same technique. So let's say we have the first derivative of vector r with respect to t dotted to the first derivative of vector r dotted to with respect to t. We take the dot product and then we will take the time derivative. So here we'll call this as vector valued function 1 and this is function 2. So this will be equals to, first we will take derivative with respect to t of our first function. So that's dr vector with respect to dt, the derivative taken with respect to t, and then dotted with our second function, which is simply dr vector over dt. Plus we'll take the first function, which is dr vector over dt, and dot it to the derivative with respect to t of our second function, dr vector over dt. So this is equals to, so we have the second derivative of vector r with respect to t dotted to dr over dt, and the same thing is happening in the second term as well. So this will be simply 2 times. So that means derivative with respect to t of the dot product between the first derivative of r with respect to t with itself. So that simply equals to 2 times second derivative of r with respect to t dotted with the first derivative of r with respect to t. So let's label this as equation number 2. The only reason we are doing this is so that we'll start now with a given equation. So here we are provided d squared r vector divided by dt squared. So that's equals to negative n squared times r vector. So what we'll do, we will take the dot product on both sides with 2 dr vector over dt. This will be dotted to, we have d squared r vector over dt squared, and on the right hand side we have n squared times, so we have r vector, so this will be dotted to dr vector over dt. Now why we have done it, so that we can use equation 1 and 2 and we can rewrite this one as equivalent to derivative with respect to t of dr vector over dt dotted with dr vector over dt, which will be equals to negative n squared times. Similarly, we can replace this with equation number 1. So we will have derivative with respect to t of vector r dotted to vector r. Fine. Now integrating this original equation on both sides with respect to t, that's the same as taking the integration with respect to t of this particular equation. So that means we have integration. So this is going to give us dr vector over dt dotted to dr vector over dt, which will be equals to negative n squared times r vector dotted to r vector plus some constant of integration, which is c1. This is simply a scalar. Now dr vector over dt dotted to itself, that's simply dr vector over dt squared, which will be equals to negative n squared times r vector squared, plus the constant of integration c1. So that means when we integrate the given original equation, we should get this new equation, which is first derivative of r with respect to t squared equals to negative n squared times r vector squared plus the constant of integration c1.